interest of time, we'll move on then. So the next speaker in this venue needs no introduction, but I'll introduce him anyway. Professor Zhang is chair of the Department of Biomedical Engineering here and one of our hosts. And so we look forward to his presentation on remuscularization of injured ventricle has been achieved in rodents. What's next?
So I will take the opportunity to report to you that in the next 15 minutes, what we are going to do, use your money for the next 7 years. So as many of you know that we are founded by this PCTC hub, and we are the collaborator are the UAB investigators, Wisconsin Medicine and Duke. You'll hear more from Tim Camp and Nina Bosak. And I want to convey that Danny Buxton want to continue to have this Jumpstart collaborating grant. So the main goal is to maintain the community together. So we have PCBC 7 years, and I'm very happy to see that the PCBC community continue and expand. And going forward, we'll have the community from the collaborator from not only United States, from Canada, from the Europe, from the Japan. We have the Doc Sawa's group giving the talk tomorrow also. So it is very exciting to see really the science and the engineering convergence, what it bring to us. So I will try to present only unpublished data for the U01 grant. With just luck, we actually had a few published in the last few weeks. So seeing the only presenting unpublished data become a lie, but we'll share with you the exciting new data. So we all want to regenerate this myocardial infarction, lost myocardial mass due to ischemia injury. And with my lab staff and colleagues, day and night work, we actually, in rodent, we achieved the regenerate myocardial muscle in rodent heart. And the real question is what we can do and what we will do in the next 7 years to how to best use of your money. Okay. So I will talk about making the cardiac regeneration happen, roadblocks to overcome. That's the 4 major problem in our field in the cell therapy, cardiac therapy. Listed here are the low engraftment rate, the increase of arrhythmic potential, the integration between the graft and recipient heart, and to make larger, thicker, and clinical relevant size of myocardial tissue equivalent, meaning that the functional tissue, we have Dr. Pool's lab presenting the functional tissue. We need to have cardiac tissue with vessel, with muscle, with even the new nerve contribution also. That's the goal. So with limited time today, we'll only talk about the roadblock number 1, that is the low engraftment rate. So the strategy we are listed here are using the human iPSC derived iPSC, use the CRISPR-Cas9 to knock out human HA class 1 and class 2 to generate the universal cell line. And number 2, to turn back the clock to promote the myocyte re-enter the cell cycle. And number 3, we try to fabricate larger, thicker myocardial tissue equivalent patch using the iPSC-derived tri-lineage cardiac cells. So this slide illustrates the typical result of HA class 1 knockout by knockout the beta-2 microglobulin, the guiding RNA sequence 1 and 2 showing here. The sequence 2 was being able to successfully knock out the beta-2 microglobulin. Beta-2 microglobulin, as you know, is the key protein in the HA class 1 protein complex. Once this one is knocked out, the HA A class 1 have no functional effect. Similarly, we knock out the HA class 2 transactivator. So both HA class 1, class 2 knockout that was successful. And then next question is the new generally engineered cell line, whether they are maintain the stemness. This shows the 3D culture of iPSC-derived myocyte that beating in the bioreactor. It's continue beating for days and weeks without actually at necrotic core. So this is actually 1 millimeter, about 1 millimeter, 200,000 iPSC-derived myocyte that was class 1, class 2 knockout. We transport these spheroid to Wisconsin Medicine. These spheroid continue beating in the kidney capsule, beating in the ear. So the ear is beating, and in the kidney capsule it's beating also. So it's all the text dollar. We want to find out what is going on with this spheroid. It's a survive capability that without necrotic core. So we have a few postdocs examining why I was expecting to have a necrotic core by this 1 millimeter in size of the spheroid, but it continues beating without significant necrosis. So anybody interested in apoptosis, necrosis, and Geraldine is here, we'll send it to you. We can send to Wisconsin, we can send to you to examine the mysterious survive capability of this spheroid. Now we tested the privilege of immuno privilege, as shown here, the Y type. We co-cultured the spheroid with human peripheral blood mononuclear cell at day 5. The class 1, class 2 knockout avoid with the peripheral blood immunocells attack. So these spheroids continue beating, as opposed to Y type at day 5, they are shrinking, but it's still beating. If you look carefully, they're still beating. So for whatever the reason, they have the immunoprivilege as shown here. And that's probably, in reality, that's more complicated as A, B, C, E, F, G subtype in the class 2, class 1. But that's this continues for quite a few more days. So the data, your text dollar derived, we are open to collaborate. We can ship to Wisconsin Medicine, we can ship to anywhere in the country to examine the survive capability. And the plan is the grant, we are using the Tim Camp and Jamie Thompson lab, this HIM model that is humanized immunosystem mouse model. It's immunodeficient mice receive cord blood transplantation at the same time with the harvested neonatal thymus. So the repopulating human cord blood cells in the mouse model are educated by the thymus, so they are mature immuno cells. So we can test the immunoprivilege or immunomodulation. So this is truly unpublished data. The next few data are published recently, but I still share with you anyway. So this one is about the turn back the clock, promoting the myocyte re-enter the cell cycle. So if we know that 4 weeks after the transplantation, the engraftment rate is 1% or 0.1%, depends on how do you deliver it, what model use. But in any case, it's 99% of cells are gone a few weeks after the transplantation. But if we can make the 0.1% or 1% of cell re-enter the cell cycle, then then we can have significant graft. It's just like if you think about the hematologist does the bone marrow transplantation, you just need to have one cell survive, we can repopulate the circulation. So this is the thought. We start this project. Wook Zhu is here with lead this project. He will talk more about that tomorrow in detail, but I just show you some data. This is the human cardiac fibroblast-derived iPSC transfected with the MHC-driven cyclin D2. And cyclin D2 play a critical role in the cell dividing. And only the cells, because of the MHC-driven, so only the cells differentiate to my side will have the D2 overexpression. As shown here, the Western blot showing the clone 3 is successfully overexpressed D2, and in vitro showing the cyclinosis and cell dividing significant increase. So this is the showing week 4 in vivo, 4 weeks after the transplantation, the wild type, the human cells in the rodent heart as shown here, the human specific troponin T showing in red and brown, which is significantly increased in the cyclin D2 overexpressed the myocyte transplantation as shown here. These significant piece of the human tissue regrow in the rodent heart. And this is 1 month, and that got out last month in Circulation Research, and specifically these are the human-specific nuclear antigen shown in white, all nuclear showing in blue, and so the human-specific troponin T showing in red. So this is a significant piece of the regrow of remuscularize the injured muscle in the rodent heart. So this is 1 month, and this is new data, 6 months. A few weeks ago, that's 2 weeks ago, we sacrificed another group of animal. So this is the rodent heart, the ALD ligation, the thin piece of scar replaced by a red piece, human-specific troponin T. The injured myocyte is replaced by this thick piece of human muscle cells. So now that's why the title is said, we remuscularize the injured left ventricle is achieved. What is the next? So I personally will have bias. I think if this piece of tissue regrow in the injured heart will generate problem, will generate arrhythmic problem by the re-entry arrhythmia when the action potential calcium signal pass through the interface with pass through the grafts will signal re-entry cause arrhythmia. Or this piece of tissue, they beating spontaneously in the petri dish, they can cause the ectopic center also. But we cannot examine this arrhythmic problem in the heartbeat 600 beats per minute. We have to be able to reproduce this piece of result in the pig heart that beats less than 100 beats per minute. So that's the ongoing project. We will try to regenerate this piece of injured pig heart with ALD ligation, and then we will have our EP team to examine the propagation pass through the interface of the recipient heart to the grafts, and whether it's the arrhythmia caused by re-entry arrhythmia or ectopic center. So finding the problem is just the step one, it's just the beginning. The real challenge, we actually need the community to help to make the myocardial tissue equivalent propagation speed similar as the recipient heart. So these tissue, the calcium propagation in this particular tissue in vitro is about 15 centimeters per second. in the native heart, naive heart is 60 centimeter per second, and the people best in the field is Nine Bosak. He is here. He will talk more about that. The speed reaches 30 centimeter per second. So, but it's still half of the naive heart. So there's a reason for re-entry problem. So then now we need to have the engineer come in to engineer this piece of tissue to have the relatively close to naive heart propagation speed to prevent the re-entry, or we can manipulate the iPSC or myocyte to prevent the ectopic center cause the arrhythmia. So that's the plan going forward. In the last minute, I'm going to show you another piece of work that's Lincoln head-on address the problem of the all the engineered tissue are small size. It's applied to rodent, but it cannot be useful for the large heart. So this is use the human iPSC-derived cardiomyocyte, endothelial cell, smooth muscle cell to fabricate the myocardial tissue equivalent, as shown here. This is 2 by 4 centimeter in size and 1 by 2 millimeter in thickness. So this is probably the largest so far in the literature relevant to the clinical application. So each pig heart receive 2 pieces of these fabricated myocardial tissue, 40 millions each heart. This was published last month in Circulation 2018. I just share one data. The details are in this paper, but for the functional tissue perspective, we all know that myocyte need the endothelial cell in the neighborhood to function well, and this piece of data showing that when we fabricate these myocardial tissue, with and without endothelial cell and smooth muscle cell in the structure make a big difference. This is a 4th generation per myocyte, normalized to per myocyte. So if we compare to cardiomyocyte, endothelial cell, smooth muscle cell in the open bar versus the myocyte only in the field bar, the 4th generation is about 1.2 millinewton per piece of tissue. But when we normalize, because this total number of cells are the same, so the myocyte only 50% in the 3 lineage cardiac cells. So when we normalize per myocyte, the fabricated tissue with endothelial cell and smooth muscle cell in the neighborhood, the contractile 4th generation is almost twice as much as the myocyte only. So myocyte need endothelial cell in the environment to function better. This is about 1.2 nanonewton per myocyte. This is probably one of the best quality in 4th generation in this size of the fabricated engineered tissue. So again, check Gall et al. Circulation 2018. So with limited 15 minutes, I just try to convey our plan for the next 7 years, next 6 years by now. And I want to take the opportunity to thank my colleagues and associate, showing here the Wook is here, did the D2 work. Lin Gao is back there, did all the dynamic culture of fabricated larger, thicker, clinical relevant myocardial tissue equivalent, and collaborators including the University of Minnesota, Dr. Gary, Dr. Ogle, and Wisconsin Medicine, Dr. Inger and Dr. Camp, UAB collaborators, Tim Towns, Jack Rogers, Dr. Fass, Wilcott, and Dr. Bosak in Duke, including name not showing here are the Victor Zhao and Howard Rockman are the collaborators, and Dan Gary and Suman Prabhu are here also. So I'm glad every one of my collaborators are all here. This your money again is all the NIH grant, and you won the PCBC and PCTC here. Thank you very much.
Okay, thank you, Jay. If Roberto could come up and get his slides ready. Jay, you want to do one quick question while Roberto